Okay, kiddos, today I'm going to tell you about Objective 4.1, which is acids and bases. I'm going to talk about a bunch of stuff today. First, just going to start a little bit about what are some acids and bases that you might actually be familiar with. They're really very common, and a lot of them around us. If you look at the acids things, lemon juice, vinegar, proteins, we don't think of that. Protein is like, the meat part of meat. Bases, a lot of cleaning things here. Windex, baking soda, soap. These are all things that we see on a pretty regular basis that would be considered acids or bases. The way we define something as an acid or a base, we call the pH scale. pH scale basically runs from numbers 0 to 14. Easy way to compare different acids and bases. The acids are on these small numbers, so from 0 all the way up to 7. You notice at 7 we hit what's called neutral, and then anything above 7 is a base. Okay, and this is showing us how strong an acid or a base is. We measure pH. P is a math term. The H actually stands for H plus ions. So this is what we call a logarithmic scale that measures how many H plus ions are dissolved in a liquid. The more H plus ions you have, the stronger an acid and the smaller your number gets. If you have a real small amount of H plus ions, then your acid gets really weak, or we could also say it becomes more of a base, and the bigger your pH number gets. So pH is kind of an inverse scale. The bigger the number, the smaller the concentration of hydrogens in our liquid. Another thing to note, it's a logarithmic scale, which means if you go from a 7 to a 6, that's actually a factor of 10. So an acid of 1 is 10 times stronger than an acid that has a pH of 2. And an acid of pH of 1 is 100 times stronger than an acid that has a pH of 3, because it's 10 times stronger from 1 to 2 and 10 times stronger from 2 to 3. So 10 times 10 gives us 100. Easy way to recognize acids, and this is one of the things we are expecting you to do for Objective 4.1, is that acids almost always have hydrogen as the first letter in their formulas. And if you're looking at a chemical equation, a chemical reaction, acids will actually lose their hydrogen. We call that donating. They donate their hydrogen to another molecule. So some examples here: HCl, H2SO4, HNO3. Notice all of these chemical formulas start with an H. The H is actually the positive ion, and the NO3, SO4, and the Cl is the negative ion. So an acid is, for most cases, a molecule that has H as its positive ion. There's this stuff that we can use to test acids and bases called litmus paper. And if you dip a piece of this litmus paper into a liquid, if it's an acid, it's going to turn that paper a red color. When acids are crystals, if you put them in water, when they dissociate, which is just a fancy way of saying dissolving, when acids dissolve, they break up into their positive and negative ions. And like I said earlier, the positive ion is H+. So an example here, this is actually showing hydrochloric acid, HCl, dissolving in water. So equation-wise, we would say it's mixed with water, H2O. And when this happens, the hydrogen part of the HCl actually chemically bonds to the H2O. And when you get that, you get this weird H3O ion. It's called hydronium. And then you have the Cl minuses left over. Well, for most things, we basically say H3O plus. Yeah, we know it's there. But for all intents and purposes, it acts like it's just an H plus ion. So when we say they dissociate to make H plus ions, or when they dissolve to make H plus ions, we're really saying they will react with water to form H3O plus, but when you mix this with other chemicals, it acts like it's just an H. It's kind of a weird thing. For bases, some more patterns here. Again, we expect you to know this for objective 4.1. All bases receive an H plus ion. Okay, they're a chemical that the acid donates its H plus ion to. And a lot of these in their chemical formula, you're going to see the negative ion is an hydroxide ion, an OH minus. If you take that same litmus paper that turns red in acid, if you take a litmus paper and put it into a liquid that's a base, it actually turns the litmus paper blue. So, easy way to remember that. Blue, blue, base. Litmus paper turns blue in base. A couple of bases here. Notice the negative ion, OH. The negative ion is an OH. These will, when they're dissolved in water, break up into Na pluses and OH minuses. And this one breaks up into Mg 2 pluses and 2 ions of OH minus. And it's these OH minus ions that will actually receive the H plus. Okay? Now NH3 is kind of a weird one. So there are some exceptions to this rule. NH3 is ammonia. Used a lot of times in household cleaners. Has a really, really nasty smell. And if you take ammonia and mix it with an acid, it will take this H plus and it actually becomes an ammonium ion, which if you look on the back of your periodic tables, it's the only positively charged ion we have on there for you. Another thing to know is what we call conjugate pairs. So when an acid reacts with a base, that's a lot of times what acids and bases are used for. The acid, when it reacts with a base, will form new things. Duh. When you have a reaction, you get new things. But the weird thing in an acid-base reaction is your products are also going to be acids and bases. Okay? So if we look at this, remember this is the reactant side here. This is the ingredients. The thing that has an H to give away, which is written first in the formula, is usually our acid. And then this one, there probably was something else attached to this OH. We're just trying to simplify things a little bit. OH is a base. Okay? When these two react, one of the hydrogens from this is going to attach itself to the OH minus, and when it does that, it becomes H2O. And what you have left over here, since this lost a hydrogen, and since hydrogens have a positive 1 charge, whatever you have left has 1 less positive charge, so it's negative. And notice we have also only 1 hydrogen here. Okay? Well, if we look at this really carefully, this H2O, in this case, acts like an acid now. It's a really, really weak acid, but it's an acid. It could potentially give one of these hydrogens back to the HSO4. So that would make it a hydrogen ion donor, which was one of the definitions of an acid. Okay? If we look at this other ion, HSO4 with a -1 charge, it has the ability to take an H plus 1 ion to go back and form H2SO4. Since it has the ability to receive an H plus ion, that makes it a base. Now it's a really, really weak base, but it still has that ability. And so to show that these are related to the original products, we use the words conjugate. So the conjugate acid is whatever the base started as, and the conjugate base is whatever the acid started as. Okay, so notice the acid, when it reacts, will become a base, and the base, when it reacts, will become an acid. Okay, so definition here for you. The conjugate acid is the product, right side of the arrow, that received a hydrogen. This H2O used to be OH minus. So it receives that H plus 1, now it becomes H2O. Okay, and originally it was the base. The conjugate base is the product, again the right side, that lost a hydrogen. So if we compare the HSO4, it used to have 2 hydrogens. So this is the thing that lost a hydrogen. And originally, it was the acid. Okay? If you look at this one, HNO3, hydrogen in front, that's a dead giveaway, it's an acid. Okay, now remember NH3 was a weird one, but we know it's a base. That's just one you're going to probably have to memorize. And then if we compare the before and after, notice the HNO3 became NO3 minus. Okay, so this is our conjugate base. It's the product that lost a hydrogen. NO3 used to have a hydrogen attached to it. Now it doesn't, so it lost that hydrogen, and it was originally the acid, right here. Okay, so that's our conjugate base. If we look at NH4 plus, it is the product that received a hydrogen. If you compare the before and after, NH4 plus used to be this NH3. If NH3 gains a hydrogen with a +1 charge, it becomes N with 4 hydrogens, and now you have that extra +1 charge. So that makes it the conjugate acid. Okay, so let's see if you can try one. I'll give you a few seconds here. Maybe you just want to pause the video. Identify what's the acid, what's the base, and then what would also be the conjugate acid and the conjugate base. This one's a little harder. Notice you have H at the beginning of both of our reactants. So this one, you got to really look at the products. One of our products is H3O plus, the other product is H2PO4. Well, this one's a little easier to see. H3O plus, excuse me, used to be H2O. Okay, so that means that H2O received a hydrogen to become H3O plus. And notice this product, H2PO4, used to be H3PO4. Notice it lost a hydrogen. So that makes it an acid. Go back to those definitions you wrote down for acid and base. The thing that gives away a hydrogen is the acid. The thing that takes the hydrogen is the base. Okay? So which of the following is your base? I already told you. H2O. How about the conjugate acid now? If H2O is our base, remember it becomes the conjugate acid. The base becomes an acid. So whatever H2O becomes, right here, that's going to be our conjugate acid. So H3O plus. Let's try another reaction. So if you could write this one down. HBr plus Cl minus reacts to form Br minus plus HCl. So which of the following in this reaction is your acid? This one's a little easier. Remember, an acid, look for the hydrogen written first. And it's only going to be on the reactant side. If it's a product, that's always going to have the word conjugate in it, little hint. So the acid, HBr. Which is going to be the conjugate base. Remember, the acid becomes a base after it reacts. So whatever your acid becomes as a product, it's going to be the conjugate base. So if we look at HBr, we have Br minuses over here. If HBr is the acid, it is giving its hydrogen away. It's donating this hydrogen to something else. So whatever you have left after it donates the hydrogen, Br, that's going to be your conjugate base. Okay? Last thing you need to know is naming. A chart here I want you to write down. Okay, so maybe pause the video, write this down quickly, and then I'll explain a few things here. Okay, hopefully you have this written down. When it says if the ion ends in, what that means is if you look at your chemical formula, so we'll use this one first, HCl. If you look at your chemical formula, if the negative piece would have a IDE ending, so we would name this hydrogen chloride. Okay, if you don't know why it's chloride, please come and ask one of us to help you with that. If the ion should have an IDE ending, what we do is we add the word hydro in front of this in place of hydrogen. And then instead of having IDE at the end, we replace that IDE with an IC, and then we're always going to have acid. So this would be called hydrochloric acid. Another example of this is HF. If we had HF, it would be hydrogen fluoride. That's what we would have called it first semester. What we do, because it has an IDE ending, we replace hydrogen with hydro, and we take off the IDE and replace it with IC. So it would be hydrofluoric acid. If your negative ion, the negative piece, which is always written second, if that has an ATE on the ending, okay, then we change it to have IC, or IC. Now notice there's no hydro here. Okay, so if you look up PO4 on the back of your periodic table, on those list of ions on the back, any of those that have an ATE on the ending, if they have hydrogen as their positive part, what we do is we take off that ATE and we change it to IC. So this is phosphate. We take off the ATE and replace it with auric. So this would be phosphoric acid. Now notice there's no hydro. It's just phosphoric acid. If the negative ion, which again you would find on the back of the periodic table, this is SO3 is sulfite. If it has an ITE ending, you replace it with OUS. And notice again there's no hydro. So this would be sulfus acid. Now there's a couple things that chemists have done for who knows how many years to help them remember this. In the cafeteria, you ate something icky. If your negative ion ends with an 8, it's going to have an IC ending. In the cafeteria, you ate something icky. And for the us, there's an old saying, bite me. I think I've said it a few times to a couple of you. Bite me goes to bite us. Okay? ITE ending has an OUS ending. Okay? So a couple of ways for you to remember your naming rules. Now we will give you chemical formulas and we will expect you to try to remember these. So just remember, in the cafeteria you ate something icky. ATE becomes ick. And bite me becomes bite us. ITE has an OUS ending. And if it's not one of those two, if it has an IDE, then you slap a hydro in front of it and ick. So, some examples. If you look up CrO4 on the back of your periodic table, it's chromate. I ate something icky. So this would be what? Pick carefully. That's right. Chromic acid. Notice no hydro. Only have hydro if the negative ion has an IDE ending, which we don't have here. HClO2. If you look up ClO2 on the back of your periodic tables, you'll find it is chlorite. Ite. Bite me becomes bite us. ITE on bite us. So which of these do you think it's going to be? That's right, chlorous acid. How about this one? H3N. We would name this hydrogen nitride. If you have "ide," that's right, you're going to need the hydro, and the ending becomes "ic."